Oake, and I'm a student at Athabasca University, and I'm currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos I've been posting on the course forum so far, you'll know that I'm going through the SparkFun Inventors Kit Guide and showing how I've done certain projects. So in a previous video series I did Project 1 and the 4 circuits associated with Project 1, and in this current video series I've started to go through Project 2, which has 3 circuits. So in the last video we went through circuit 2A, the buzzer, which is highlighted in yellow here, which basically introduced you to the basics of sound generation. I showed you a piezo buzzer and showed you how that worked. We used the tone function to produce different frequencies in the code, and we also did a coding challenge in addition to the regular circuit. In today's video, hopefully we're going to get through circuit 2B, digital trumpet, and circuit 2C, Simon Says game. But what is circuit 2B, digital trumpet? Well, that builds on the previous circuit, 2A, the buzzer, by using multiple buzzes and buttons to create melodies. Here we'll discuss the use of arrays to store musical notes and how to implement tone in combination with for loops for playing melodies. Now, we did do a little bit of that in the previous code, especially in the coding challenge, but we'll do that further today. The coding and challenge involves programming a short tune of your choice, which showcases creativity and understanding of sound generation further. And then moving on, if we get to circuit 2C, that's the Simon Says game. And I'll explain how we incorporate multiple buttons to create an interactive game. This circuit uses buzzers and LEDs for feedback based on user input. And I'll describe how to read inputs with digital read and use conditionals, if-else statements, to determine if the user's guess is correct. The game logic implementation and arrays will provide insight into handling sequences and user interactions, culminating in the coding challenge where we're going to create a 2-player version of the game. And I'll discuss best coding practices and that sort of thing. Also, yesterday we did finish the coding challenge for circuit 2A, and I just went through a couple of things that that we did in that coding challenge specifically. So I won't repeat those here. And this is the notes for challenge 2B, but we're going to get right to we've completed 2B, we've went too far. So this is where we left off. We had completed circuit 2A, which was our buzzer, and now we're on circuit 2B, our digital trumpet. So if you've been following the videos, I'm just kind of going to talk through the guide, but more or less focus on the highlights as I've made them in this guide. So circuit 2B, digital trumpet, we're going to learn about inputs and buttons as we build on what we learned about the piezo buzzer previously. So the things you're going to need, the components, are a potentiometer, piezo buzzer, 10 jumper wires, and 3 push buttons. We used the potentiometer piezo buzzer previously in the last code, but we're going to now add push buttons. So the new components are going to be buttons, which are momentary switches, meaning they're on as long as they're being actuated. As soon as you let go, they turn off. That's what makes them momentary switches, as opposed to like a light switch or something, which when you turn it on, it stays on until you flick it off. So momentary switches are best used for intermittent user input cases, like reset button and keypad buttons, like on your keyboard. Some new concepts we're going to talk about today are the binary number system. So number systems are the methods we use to represent numbers, and we're almost familiar with the base 10 number system or the decimal number system that we use every day. That's how we count, and everything is based off 10. Well, the base 2 number system is known as binary, bi for 2, and it's what computers and electronics use. And there's 2 ways to represent the state of anything, 1 or 0, so that's how binary is. Again, in the base 10 number system, we have 10 different ways to represent things. That's why we use the digits 0 through 9, and which are 10 separate digits. In the binary or base 2 number system, not the base 10, but the base 2 number system, which is what computers and electronics use, we have 2 ways to represent the state of anything, 1 or 0, which can also be on or off, true or false, high or low, 2 states. So that's typically what we've used for digital input. You might remember saying that digital input is typically 2 states. putting away pulse width modulation for a second. And there are 14 digital pins, and digital inputs are used for determining if a button has been pressed or if a switch has been flipped. Because again, we can use, just like we previously used digital outputs, well, we can use digital inputs to see which one of the two states the input pin is on. So if we have a button hooked up to a digital input, we can see if that button is low or high, 0 volts or 5 volts. And that can help us do some useful things. Pull-up resistors are another concept we're going to be talking about today. And basically, a pull-up resistor is a small circuit that holds the voltage high, 5 volts, on a pin until a button is pressed. So basically, when you have a button, you might have what's called a floating state, where the state of that the pin reads, that the button's hooked up to, might sometimes read anywhere between 0 and 5 volts and float, which, if that does that, it's not good for your program, because obviously you're listening to that pin, that digital input, for a reason, because you want to do something when the button is pressed. But if the state is floating, it's going to appear to have been pressed different times, just based on the electrical signal noise or whatever's causing the signal to float. So we often use either pull-up or pull-down resistors, but in this case we're using pull-up, so we'll talk about that, in order to pull up the state of that digital pin to 5 volts, to keep it at high all the time. And it'll be high until the button is pressed, at which point the state will go low. So we will be able to do something in the code. We'll do digital read to find out what the state of that digital pin is, and if it's high, it means it hasn't been pressed, because we're holding it high by default. But if it goes low, it means the button's been pressed. So the most common place that you will see a pull-up resistor is when working with buttons. So again, a pull-up resistor keeps the button in one state until it is pressed, and in the case of a pull-up resistor, it pulls it up to the 5 volts high and keeps it in that state until you press the button, at which point then you will read a digital low. So the RedBoard has built-in pull-up resistors, and I believe they're at 20 kilo ohms on each of the digital pins. And you can activate them just by calling the pinMode function. And normally you'd call the pinMode function passing in 2 arguments, the first one being the pin that you're setting up as an input or output, and then the second argument would typically be input or output, indicating if this pin is for output or input. But in the case of input, instead of putting the keyword input, all uppercase, you put the keyword input _ pull-up, still all uppercase, and that creates an input, that creates the pin as an input, but activates the internal pull-up resistor. Alternatively, you could just create a pull-up resistor in code, or in hardware, by physically putting a resistor between one of the button terminals and the 5 volt power rail. So as usual, this is the guide provides good schematics and diagrams for hooking up. So this circuit looks fairly similar to before, in the sense of we still have the piezo electric speaker hooked in, with the positive end of the speaker connected to digital pin 10. Again, it could be hooked up to any digital pin, but it happens to be digital pin 10. And the ground, instead of hooking it directly to ground, we've hooked it up through the potentiometer, using it in this sort of configuration, coming in through one of the terminal leads of the potentiometer, and then having out of the wiper of the potentiometer hooked into the ground rail, which is hooked to the ground of the microcontroller. This setup allows us to control the amount of current going through the buzzer, which allows us to control the volume. If we didn't have this setup and we directly just had hooked this pin directly to ground, we would be getting the full 5 volts of current, which would allow full current through this speaker, and that would be at full volume. By using the potentiometer as a volume control, we can lower that volume and adjust it. And then we've got 3 momentary switches hooked up, or 3 buttons. Each button has 2 terminals, well, 4 altogether, but these 2 are connected, and these leads are connected. But these 2 terminals are not connected unless the button is pushed down. So we always have one end connected to the ground rail, which ultimately connects to the ground of the microcontroller, and the other ends are connected to digital pins that, again, we're using as inputs. And in this case, we have the red, yellow, and green buttons on digital pins 2, 3, and 4 respectively. So again, internally, these pins are always connected. So these two pins are connected, and these two pins are connected. These are not connected unless the button is pushed down. And buttons are not polarized, so you don't have to worry about that, but you do have to make sure you're connecting them correctly in the breadboard. So this is what your circuit will look like. So without further ado, we'll quickly look at the overview and then get to the code. So what this program does, it just checks to see if the first button is pressed. If the first button is pressed, it's going to play the frequency for the note C. And if it isn't pressed, we're going to skip to the next else if statement. And then if the second button is pressed, we're going to play the frequency for E. If it isn't pressed, we're going to skip and go to the next else statement. And if the third button is pressed, we're going to play the frequency for note G. And if it's not pressed, we're going to skip to the else statement. And the else statement is going to happen regardless if none of the other buttons have been pressed. So if none of the if statements are true, then the buzzer will turn off. So basically we're just going to check and see which button is pressed, and if depending on the button that's pressed, we're going to play a particular note, C, E, or G, depending on if the first, second, or third buttons are pressed. If no buttons are pressed, the speaker will be off. And then we have some code to note, but first let's actually look at the code. So, as usual, this is having some difficulty here. I'm just going to increase the font size of this code so we can go through it really good. So as usual, SparkFun has a comment just explaining what the multi-line comment explaining what the code does. In this case, we're going to use 3 buttons plugged to play musical notes on a buzzer. We also have links to the circuit diagram and this code at sparkfun.com. And so we have a bunch of variables set up. So these 3 variables set the pins for the button and the buzzer. So first key pin equals 2, second key pin equals 3, and third key pin equals 4. Again, it's always good to create variables, named variables for things instead of just using magic numbers down here. So we could just use the numbers 2, 3, and 4 directly in our pinMode functions and set those pins up as inputs, but that wouldn't be very descriptive. We wouldn't know what that meant without coming up and finding out, without looking at the circuit and being like, oh, okay, there's a button hooked up to pin 2 and 3 and 4. Similarly with the buzzer pin, we would have to look up pin 10 at the circuit and see what's actually hooked up to it. So it's always good to use variables. Typically, as I've mentioned before in previous videos, it might be better to actually use the word constant in front of it, indicating that this is not going to change, because we're not going to be changing the pin during the code. So we should really make it a constant, in which case then we could take the name and by convention make it all uppercase, separating words with underscores. I've mentioned that in previous videos, but either way, this still works the same. So again, we created variables for our 3 buttons and the pin that our buzzer pin is on. In setup, we just set up our 3 buttons as inputs, but specifically, instead of just putting the keyword input here, we input underscore pull-up. So we've set up those internal pull-up resistors. So now we don't have to add pull-up resistors in hardware. And again, the reason for adding these internal pull-up resistors is so that we can avoid having a floating state on those pins. And now the pins will always be 5 volts unless pressed. And then we set up our buzzer pin as an output. In the loop, we basically just check. We use a digital read to check if, in this case, if the first button equals low, meaning it's been pressed. Because again, it's going to be, the digital read should always read high if the button's not pressed, because we're using a pull-up resistor to pull those pins to 5 volts or high. So if they equal low, using this Boolean equals operator, the 2 equal sign, if they equal low, that means the button's been pressed. So if the first button's been pressed, we're going to call the tone function using the 2-argument version of the tone function. Remember, there's an optional third argument that will tell you how long of a duration to play the tone for. If you don't include that, you just play the tone indefinitely, and then you just have to stop the tone with the no tone function. So in this case, we're just going to play some tone on the buzzer pin of a hertz of 262. So we're going to play the frequency C. So if we look down here in the notes, note C is at 262 hertz. If the second button equals low, meaning it's been pressed, we're going to play 330 hertz. So we're going to play the frequency for note E. And if the third button has been pressed, we're going to play the frequency for note G, 392 Hertz, which again corresponds to note G. Else, if no buttons have been pressed, we're going to call the no tone function and pass in buzzer pin. It only takes one note and it just basically stops playing any tone on the pin associated with the speaker. And that's pretty much it. Very simple code. Let's upload it. So I'm just gonna okay. My computer seems to be glitching out here. We're going to do a quick technical difficulty situation. So I did upload the code to the Arduino board. I just was suffering some technical difficulty issues, which hopefully will be sorted, but don't seem to be. I'm going to restart this whole thing. So again, just bear with me, but this is I don't like to pause these videos because you know what? Any issues that I'm experiencing here could happen to you. And in this case, this is not an issue with Arduino. This is an issue with the fact I don't have a webcam, so I'm using my cell phone, and obviously the software just died for a second. But anyway, I uploaded this code, which is very simple code, to the Arduino board, and let's see what happens. Oh, I have the volume on low because again we have the piezoelectric buzzer going through this potentiometer, and I've obviously got it all the way down, which is why you didn't hear it there. So let's turn it all the way up. So as you can see, pressing the different buttons corresponds to a different frequency. So this red wire is connected to digital pin 2. I'm not sure if you can see there. Red is connected to digital pin 2, yellow is connected to digital pin 3, and green is connected to digital pin 4. So this is the first button, plays note C, note E, and the third button, note G. So that's as simple as that circuit is right there. I'm not music inclined, so that those sounds don't mean much to me, but we then went ahead and did the coding challenge for that. But before we do that, let's jump back to our guide. So the things to note in that code was we used internal pull-up resistors. So how do we do that? Well, we called pinMode as normal, passing in two arguments, the first one being the pin that we want to set up as an input or output, and then normally we pass in the key, constant keyword input or output, all in uppercase. In this case, we passed in input underscore pull-up. So it creates the button pins as input pins, but with internal pull-up resistors activated, which means we won't have a floating state. So again, to declare standard input, you use the line pinMode and pass in the arguments pin, comma, input. That's for a standard input. But if you would like to use one of the RedBoard's built-in pull-up 20 kilo ohm resistors, it would look like this. You just add input underscore pull-up as the second argument instead. And the advantage of external pull-ups, however, using them in hardware, as I said, would be that you'd be able to choose a more exact value for the resistor. In this case, you're just getting the 20 kilo ohm resistor. That's what the internal pull-up is. And then for digital input, you just do a digital read. You call the digital read function and pass in as its argument the pin that you want to read, and that will read and find out if it's high or low, what the state of that digital pin is. So again, we're checking to see if we're going to read a high on the pin, which is 5 volts, or low, 0 volts, which basically returns true or false. True is 1, which represents 5 volts. false is 0, which represents low. We're checking to see if something's equal to something, so we go is equal to. We go if digital pin equals low. This equals to symbol, which is this double equal sign, as opposed to a single equal sign, which is an assignment operator, basically lets us compare two things together. So we see, are these two values equal to one another? One equal signs means assigning a value to a variable, keep in mind. So before we go to the coding challenge, I'll just make a note about that equals thing. So here we're going if digital read of first pin equals low, and then that's basically saying, hey, we're going to do a digital read in the pin, is it low? We could have alternatively, as it said here, when we do a digital read, it returns, we're reading to see if the pin is high or low, 5 volts or low, 0 volts. But what's being returned by the actual function is true or false, 1 or 0. So automatically this is returning a true or false depending if it's high or low. So we actually don't have to check if it's low. We don't have to explicitly go equals low. Right now, when we go digital read of first key pin, this is either going to return true or false, high or low, 1 or 0. So we can just do this directly, and this will, if the digital pin isn't pressed, it will be high. If it's low, it will be low. So right now this would say if digital pin, this is expecting it to return high, but if we simply put not high, the opposite of high, which is low, and not true, the opposite is false. If we put this code does the same thing. Not digital read of first key pin is the same thing as checking if it's low. And just to verify that, let's just re-upload that code and see if we have any change in our functionality. So we can see that we just re-uploaded it, done uploading. Yeah, so done uploading now. And let's see. So you can see there's no change in functionality. So it's the same thing. Basically, if we were checking to see if something is high, we just wouldn't include this exclamation mark or this bang symbol. I'll put it back just so that we can keep the code consistent. But there you go. So that's basically the circuit 1. And now to move on to the coding challenge. And then we'll probably end this video today and we'll do the other circuit in another video. So with the coding challenge, we're going to change the key of each button. So we're going to use the frequency table in the comment section at the end of the code to change the notes that each button plays. That's one option you do. I didn't really do that. That didn't seem like much of a challenge. You're simply just changing. To do that, you would simply, instead of playing 330 hertz, which is associated with, let me just make this bigger, 330 hertz, which is associated with the frequency for node E, we would just replace that with, I don't know, 440 hertz. So we just put 440 in place of 330 and change this comment to say you're going to play the frequency for node A. That didn't seem like it was actually much of a challenge, so I decided not to do that one. So then one of the other coding challenges you could do is play more than 3 notes with if statements. So by using combinations of buttons, you can play up to 7 notes of the scale. So you can do this in a few ways. To get more practice with if statements, try adding 7 if statements and using the Boolean AND operator to represent all of the combinations of keys. So that's one way. Basically, I want to play up to 7 notes, but I only have 3 buttons to do so. So I need to make it so that when I press each of the buttons individually, it plays a note like it did this time. But then when I press, buttons 1 and 2, it plays a special note because I'm pressing buttons 1 and 2 at the same time. Or when I press buttons 1 and 3, it plays a different note. Or when I press buttons 2 and 3. So basically we're going to use logical AND to do that. And then we're going to ultimately do the same thing but with binary math. So we're going to play more than 3 notes but using binary math, which is a clever math equation to play more than 3 notes with your 3 keys, just like we're doing up here with the Boolean AND operator, but we're going to be using binary math and make an equation that helps accomplish that. So let's get right to the code. Oh, I think I might have deleted one of my programs, but that's fine. So I'm going to pull this up over here. We're going to get rid of this original code now. We no longer need it. And we're going to see what we have here. So I'm going to go fairly quick. As usual, I have a Doxygen comment, which basically just has this extra asterisk, and then we use these special tags, which just allows me to create documentation that, first of all, we can read just as well in the program itself, but it'll allow me to run it through a special program, in this case Doxygen, and create, you know, professional HTML documents automatically. And then these are all my constants for the pin assignments. So again, as I said, I prefer using constants and variables, so I put the keyword constant in front of everything. And for the names, by convention, I make them all uppercase, separate words with underscores. Again, that's convention, not a syntactical requirement. But really, I still have my 3 button pins on pins 2, 3, and 4. My buzzer is still on pin 10. And now I've added 3 more constants for 3 LEDs. So a red LED, a green LED, and a blue LED corresponding with the 3 buttons. And 5, 6, and 7 is where we have those pins. I'm just going to make sure. Okay. And then I have the frequencies for musical notes. I've just created constants for that. So note C has a frequency of 262. So again, it's the frequency for note C, and I've just created constants for that. Again, note that I use the keyword const in front of the variable. So this is a variable of type int, and we assign 262 to it, but use the keyword const indicating this will not change in the code. And that's why I used uppercase letters for convention of naming. In setup, we're basically going to initialize the button pins as inputs, the LED pins as outputs, and the buzzer pins as output. So that's all the pin modes do. So we set up the 3 button pins as inputs, but we use the keyword input underscore pull up, setting up those internal pull up resistors as well, so that the button pins will all be held high, 5 volts by default, and go low when pressed. And this eliminates any weird readings by floating point values, or floating values rather. I set up the 3 LEDs as outputs, and I set up the buzzer pin as an output. Then in loop, we're just basically going to handle the button states and then play notes and light up some RGB LED. So in the loop, we basically set up, we create 3 local variables of type bool, or for Boolean variables, for the different button states. So first key press, second key press, and third key press. These are Boolean variables, and we basically just set them by calling the digital read function on each of the buttons separately. So digital read a first key pin, if that equals low, meaning if it's been pressed, we're going to assign true to first key pressed, and we do that for both buttons. So basically, if you're pressing the button, these variables will be true for the button that you're pressing and false otherwise. And then we have some code to handle the RGB LED color. So I'm adding an RGB LED just for fun. And I created a function set RGB color that takes in the 3 arguments, the 3 button press Boolean variables, representing whether those buttons have been pressed or not. So we'll jump right to that code so we can see. So the void set RGB color again takes in 3 Booleans as its variables, and it sets the it basically says, it goes into the code, and we digitally write. We're calling the digital write function 3 times on the red LED pin first. And the second thing, we're not just writing high or low directly, we're using this tertiary statement, which basically says, the way this works, this is kind of like an if-else statement all in one little compact operator. It basically says, what are we going to write? We're going to digitally write the red state. We're basically going to check what this variable is, and we know it's a Boolean variable because we passed it in. Remember, red state, green state, and blue state are Boolean variables that got passed in as arguments to this function. So we're going to check this state. If it's true, if this variable is true, we're going to write it high. So that's what this question mark says. It basically says if this is true, we're going to write high. Else, so this colon, we're going to write low. You can Google tertiary if-else statement C++ in Google, and it'll explain this in more detail. But essentially that's what's happening here. I'm reading, checking to see if this Boolean variable is true or false. If it's true, I'm going to make it high, and if it's false, I'm going to make it low. So essentially, if this is true, I'm going to be calling digital write. If red state was true, I'm going to do digital write, and I'm going to write to LED pin. Oh, correction, LED pin, red LED pin. I'm going to write to it high if our red state was true and low otherwise. And I'm going to do that for each of the pins. Basically, if the button's being pressed, we're going to turn on the corresponding the color of that LED. And then if we go back up to the code here, after that we're going to play tones based on the button combination. So we create a local variable int combination, and it equals first key press times 1 plus second key press times 2 plus third key press times 4. So this is using the binary math method and not the if and else statements. I realized I deleted those, so I'll remake a video with those. And I apologize for that, but I've deleted that. So this is really using binary math then. We're basically taking the first button, which is in the least significant bit location, timesing by 1. The second button, which, and timesing that by 2. And then the third button, which is in the most significant bit location of the 3, and timesing it by 4. So if you're familiar with binary, you'll know with 2 states, which is how the computer works, you can represent, when you have binary, which is 2 states, on and off, and you have 3 different in this case buttons, you can represent 2 to the third different options, and 2 to the third different options is 8 options, and that would go from 0 to 7. Now 0 is just everything off, so that's one of the options, and the other thing are 7 different combinations of things we can do, which is why we have 7 different case statements. So if you're not familiar with binary, you can Google that, but I'm sure everyone taking this course is, so I won't go into that further. So basically, we use the switch statement and pass in combination, which is, what we got from this. And if it's case 1, we're going to play tone, we're going to play note C, and then break. So basically, if the red button is pressed, we're going to play note C. Case 2, the green button is pressed by itself, so we're going to play note D. Case 3, the red and green buttons are pressed. And again, the reason we don't go to just, well, what if the blue button is pressed individually by itself? Again, this has to do with how binary works. So we've kind of made that. Case 4, that's the blue button is pressed by itself. Case 5, the red plus blue button is pressed. Case 6, green plus blue button is pressed, so we're going to play note A. And case 7, all 3 are pressed, so we're going to play note B. If nothing, and the default, meaning if none of these cases were true, that means nothing was pressed, and we're just going to go no tone. We're going to shut off any sound and break. And we're just using the same play tone function that we were using before, where we pass it in a frequency, and we basically, just the play tone function is really just encapsulating the tone function. So we pass in a frequency, and then we just call the tone function, which the first argument is the buzzer pin, and the second argument is the frequency. And I'm just going to upload this code, and then I've actually got to get going to an appointment with my child, so this is going to be a video. You guys are lucky because I'm going to be ending it quickly, which is not normal. So you notice on this LED here, hey Google, stop. So I'll actually have to come back and do the demo after, because I do have to leave for this thing. So we'll end it there with that was the code walkthrough, and I'll actually upload the code fully and do the demo after, because I actually have to add an RGB LED to this as well, which I did take off the circuit for simplicity. So I'll be back to that. So when I come back in the following video, I'll just make an amendment to this video. We're going to show the circuit demo for the binary math here, and then we may go over this alternate option using Boolean AND statements. But thanks for watching. Again, this video really was just a walkthrough of the code for the code challenge, not so much a demo, but I'll come back with a demo at a later point. Thank you.